Hello and welcome to part 1 on the fundamentals. By fundamentals, I mean the fundamentals that we'll need to understand and build our AI, which is the TD3 twin delayed DDPG. Alright, so which fundamental will we need? Well, first, let's begin with the very basics, reinforcement learning, and let's just remind how this works. So this is very simple. You have an agent that is interacting with an environment, and at every time step, every iteration this agent will take as input a state representing what's happening inside the environment, the situation at a specific time, and returning as output the action to play inside this environment. And as soon as the AI plays an action, this changes the state and it reaches a next state. And then by reaching this next state, it will receive a reward which will tell the agent whether he's doing great or not. So for example, here we see a maze. Well, the state could simply be the location of the agent at a specific time. The action could simply be go left, go right, up or down. And the reward could simply be defined as 1 if the agent manages to get out of the maze, and 0 if, for example, it falls into that hole. So that's a simple way to define a reward system. Of course, for what we're going to do, our applications of training a robot on how to walk, well, the reward system is a little bit more complex, but you see the idea. The more the robot manages to walk and even run, the higher will be the reward, and the less it is able to do that, that is, when it falls or when it stays still, well, the reward will be negative. And that's therefore many rewards that the robot will get at every time step, and the goal for that robot will be to maximize the accumulated reward over time. And that accumulated reward over time has a specific name. It is called the return, and that's the fundamental principle in reinforcement learning. The goal is to maximize the return, and more specifically, it is to maximize the expected return. And I'm highlighting this because the next fundamental we will see together is policy gradient, and you're going to see that the principle of policy gradient is to directly update the weights of the AI in order to increase and maximize that expected return. We'll get to this very quickly. Another word that you need to be aware of is that the agent is called a policy, and a policy is nothing else than a function taking as input the state and returning as output the action. So that's the fundamentals of reinforcement learning. That's all you need to know so far in order to get to the next fundamental. And the next fundamental is about Q-learning. Why is that? Why is that a fundamental that we need for this twin delayed DDPG algorithm? Well, that's because Q-learning is actually one of the 2 essential parts of the TD3 model. Why is that? That's because the TD3 model will learn 2 things at the same time. It will learn the Q values, which is based on Q-learning, and it will learn, of course, the parameters of the policy, that is, the weights of the policy, because the policy will, of course, be an artificial brain, an artificial neural network, which will take as input the state and returning as output the predicted actions to play in order to maximize that expected return. And the way it is going to achieve this, we'll get to that quickly, is by learning 2 things. First, the Q values, I'll explain that right away, and then the parameters of the policy. Alright, so let's remind what is Q-learning. So this is the very basics of Q-learning, happening in an environment with a finite number of states. That's the most basic version of Q-learning. And so how does it work? Well, the agent here is going to learn what we call Q values, which represent exactly the quality. You can remember this. Q in Q-learning can be seen as quality, the quality of a couple of state and action. So let's see. For example, here we see an agent that is still inside a maze, a very simple maze, and the goal of the agent, as you can see, is to reach the final destination. And if it does, it will get the reward +1, and however, if it reaches that fire here, it will get the reward -1. And the states and actions, what are they going to be? Well, again, there are many ways to define states and actions, but here, of course, the states are going to be simply the position of the agent at each specific time. So right now, the agent is in this position, meaning the states will be this position exactly, and then the actions can simply be going up, down, left, or right. All right? So let's say that's the case. And well, what is going to be a high Q value in this example? Well, this is going to be the Q value of this state and the action of going right. Because by being in this state and by taking the action of going right, well, we get to the final destination, meaning we get to the reward +1. So the Q value not only represents the quality of a state and action couple, but also it is going to be higher when getting closer to the highest reward. You know, the more you maximize your expected return, the higher is going to be the Q value. So the highest Q value that we're going to have here is going to be the Q value of the state associated with the action of going right. Then the second highest Q values that are going to be a little smaller than this one, but still the highest after this one, is going to be the Q value of that state with the action of going right. Because by playing the action of going right in that state, in that position, well, you will get closer to the state that leads you then to the final destination with the maximum reward. And then we also have this Q value of the state and the action of going up that will be very high as well for the same reason that it is getting closer to the maximum reward. However, this Q value of that state, that same location and going right, will be of course the lowest one because it is leading to the worst reward. So that's exactly how you should see the Q value. The Q value is a function taking as input a couple of state and action and returning as output a number, which is going to be higher the more the action played from the state is getting the agent closer to the optimal reward. All right, so that's the intuition of Q-learning. And then you have the whole algorithm explained here. So you're going to initialize all the Q values for all the different couples of states and actions to 0. And then you're going to repeat over many iterations the following steps, starting with the selection of a random state, like having the agent starting in any cell here. Then from that state, you're going to play a random action. You reach the next state. Let's say that random action is going up, so you're going to reach that next state here, and you get the reward, which is here still 0, or STAT. Then you compute what we call this temporal difference, which is the difference between two important elements, this first element and this element. So this first element, the reward plus the maximum Q value of the next state over the actions, represents in fact the optimal immediate reward. Because indeed, since we understood that the Q value represents the quality of your couples and states and actions, well, by getting the maximum here of the Q values, well, that element represents in some way an optimal immediate reward. And that's why you will see later on that it will actually be the target. In deep Q learning, which is the next fundamental, you will see that this element is exactly the target that we will want our predicted Q values to be as close as possible, because this represents an optimal reward. And then the second element is the Q value of the current state and action. And later on, you will see that this will be the prediction in deep Q learning. We'll get to that later, but for now, let's explain what is the use of this temporal difference. Well, to understand the use, we need to go to the next step, step 5, because indeed, in step 5, we update the Q value by applying this very famous equation called the Bellman equation, which will simply increase the Q value at the previous step by this temporal difference multiplied by the learning rate alpha, which is usually equal to 0.9 or 0.95. But basically what this means is that the higher the temporal difference is, that is, the more you're able to find that optimal immediate reward, well, you will increase the Q value, which is the overall goal when working with Q learning and learning Q values. You want to find the highest Q values. You want to find the states and actions that leads you to higher and higher Q values, because getting higher and higher Q values will get you to the optimal reward, the optimal accumulated reward. And so that's the whole purpose of this temporal difference. We're looking for the large ones in order here to increase the Q values and get the states and actions having the highest Q values. And then at some point, so you will repeat these steps over many iterations, and at some point your Q values will converge and you will get some smaller and smaller temporal differences because you will already get the high Q values, therefore reducing, that difference between the optimal Q values and your current Q value of the current state. And so that's the training process. And then once the training process is done, once you run all these iterations, well, guess what the agent is going to do? Well, very simply, it is going to play the action that has the highest Q value when being in that state. So for example, if the agent is here, well, you understood that the highest Q value is the one of this state and action of going right, and therefore it will go right. All right? So what you must remember here with this first fundamental of Q-learning is that the agent is learning some Q values, so that the higher is the Q value, the more the agent will be in the right states, playing the right actions that will get it to reach the optimal return.
Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.